Hello, I am Diptarup, and in this lecture, we're going to learn a little bit more about Intel's Data Plane Development Kit, or what we call DPDK in short. The prerequisite for this lecture is a previous lecture on kernel bypass delivered by Rinku and Priyanka. While that lecture handles the theoretical aspects of kernel bypass and DPDK, this lecture is focused more on the implementation or hands-on approach on how to code a DPDK application, how to install and compile DPDK, and what are the designs that developers follow while coding and running a DPDK application. So in this lecture, we'll first talk about the implementation designs, then we'll see how to install and compile DPDK, and finally, we'll give a demonstration by running a simple DPDK application. So first, let me talk about the implementation designs. Any DPDK application can be broadly classified into either of the two designs. It can be either run to completion design or it can be pipeline design. So what is a run to completion design? In this design or in this model, whenever the NIC receives a batch of packets, any one of the cores running the DPDK application receives those packets, it processes those packets, and then finally sends them out via the NIC. And this cycle continues. That is, we receive a bunch of packets, we process them, transmit them out, then we receive the next batch, we process and transmit, and this goes on. Whereas in the pipeline model, there are at least two cores involved. So for the time being, let us assume that there are only two cores. So there is one master core and there is one worker core. What happens is, whenever the NIC receives a batch of packets, the master core receives those packets in the user space from the NIC and then transfers those packets to the worker core. The worker core will now receive those packets from the master core, process them, and then transmit them out via the NIC. And this cycle continues. That is, whenever there is a bunch of packets, the master core receives them and transfers to the worker core. The worker core will process those packets and then send them out. Note that while the worker core here is processing the packets, the master core is free to receive more packets from the NIC. Whereas this was not possible in the RTC design. Why? Because if whenever a core is processing, it is in the process state and it cannot receive the next batch of packets unless it transmits the current batch. So it transmits the current batch, only then it can receive the next batch. But the master core in the pipeline design is free to receive packets while the worker cores are processing them. So let us go into a bit more detail about both these models or both these designs. First up is run to completion model. So let's assume the NIC receives an UDP packet. When it receives an UDP packet, it is sent to any one of the RX queues via RSS on NIC. As you may recall, RSS or receive side scaling was discussed in the previous lecture on kernel bypass. So when this packet is sent to any one of the RX queues, any one of the cores takes up this packet in the user space, processes the packet. By processing packets, I mean removing or adding any headers, manipulating the data, etc. And then transmit those packets out via the TX queues. Similarly, any other packet may be redirected to any one of the RX queues, and any one core will take up that packet in the user space, process, and then transmit it out. Scaling or launching multi-core applications is very easy. We just have to launch the same code across different cores. And the packet distribution is done in the NIC itself via RSS. In the pipeline model, whenever a NIC receives let's say the NIC receives an UDP packet as earlier, so it is then redirected to any one of the RX queues. Now, any one of the master cores will receive this packet into the user space. So we have this UDP packet in the user space now, and then the master core will distribute or transmit or transfer this packet into one of the worker cores. So DPDK provides data structures for efficient inter-core communication. So here we can see a ring. This is essentially a doubly ended queue, which is provided by DPDK for efficient inter-core communication. So once the worker core receives these packets, it will process and then send them out. So any other packet will be received by any one of the master cores. Similarly, it will be sent to any one of the worker cores, and then they will process and send them out. Note that RSS on NIC is not compulsory. That is, even if all the packets are redirected to only one RX queue, the master core or the master cores still can distribute the packets to different worker cores in the user space. So a brief comparison between both the designs. Both RTC or run to completion and pipeline are easily scalable. So we saw how we can scale RTC design. We just have to launch same code across multiple cores. Whereas in the pipeline model, if there is RSS on the NIC, then multiple master cores can receive the packets and then transfer via rings to multiple worker cores. Even if there is no RSS, one master core can receive, and then it can transfer packets to several worker cores, and we can scale our application. So one advantage of run to completion is there is less user space processing over it. That is, there is no inter-core communication, which is there in the pipeline. However, on the other hand, the pipeline design doesn't require any hardware support. That is, RSS function on the NIC to distribute packets to other cores. So if there is no hardware support in the run to completion model, then only one core will receive all the packets and our application won't scale. Now that we have seen the two different designs, let us see how to install and compile DPDK on our machines. But first, we have to check whether our hardware supports DPDK or not. So the link is given in the slides. You can check that out. I have just opened the link. I will show you an example. So DPDK is supported only on these NICs and on these CPUs. So you can go to this page and check whether you have the hardware that supports DPDK or not. So if your server, if the machine supports DPDK, then installing and compiling DPDK is simple. We just have to follow a few steps. First, we need to clone the DPDK repository from their GitHub page, and then we need to run the following steps. So there is already a DPDK setup.sh script provided. So we'll run that script, wherein we'll compile the drivers and any applications we are writing. Or there are also several sample applications provided that will also be compiled while we compile the drivers. Once the compilation is done, then we'll insert this IGB UIO kernel module, or what is actually the pole mode driver. Then we'll bind our drivers or bind our interfaces, the NIC interfaces, to the DPDK. note that once we bind our NIC interfaces to DPDK, we cannot see them normally. For example, if you type ifconfig, there is a list of interfaces shown. However, if we bind one interface to DPDK, we cannot see it via ifconfig. So once the interface or the NIC is bound to DPDK, we'll then reserve huge pages and we are done. Now we'll run our application. We can run our application and see like whether our code is working or not. Let's look at an example. So here we'll be showing the L2 forwarding sample application. The link is again provided in the slides, and I have opened the tab already. So this L2 forwarding sample application, what it does is it will just, so there are two servers involved. I'll explain the setup. So what it does is it just receives a batch of packets, a bunch of packets. It swaps the MAC, like it swaps the source and destination MAC, and then it will forward those packets back to the server from where it received. That is, so let me explain the setup. So there are two servers. There is a load generator, we'll call that server A, and there is a server B which is running our L2 forward application, and it runs on DPDK. So what happens is this load generator, it will generate packets, it will generate IP packets with Ethernet headers with source address is the MAC address of A and destination is the MAC of B. This packet will come to server B, and then via DPDK it will receive these packets in the user space. So once we receive these packets in the user space, the L2 forward application will swap the MAC. Note that earlier the source was MAC of A and the destination was MAC of B. Now the source is MAC of B and the destination is MAC of A. So we'll swap these MACs and we'll transmit these packets out via the NIC. So we'll only be manipulating the layer 2 header. So for layer 3 onwards, we are not concerned in this L2 forward application. Of course, there are other applications and you can write your own application where you can manipulate IP headers or L4 headers or the data. But in this application, we'll just be swapping our MAC addresses. So once this packet is out of the NIC, we can see here that source is MAC B and destination is MAC A. It reaches the server A, that is the load generator. So this is the summary. So the Ethernet is swapped, the MAC addresses are swapped, Ethernet header is manipulated, and then those packets are sent back. And this process is continued. Load generator will continuously send packets. Our application will swap the MAC and then return those packets. So let me give a demo first. In the demo, I'll be using certain command line arguments. So don't be startled by that. I'll explain them in the next few slides. But let us look at the demo first. So here is our L2 forward application. I'll just start it. And okay, so that L2 forward application is started, and I already have started the load generator. So here I'll generate load for this demo. Number of CPU cores. So let me use 600 byte payloads. Number of seconds, I'll use 30 seconds. I'll explain you. Yeah. So after 30 seconds, the total number of packets sent is this, and throughput is around 39 Gbps. So here it received around 939 19 million packets, I guess. It didn't receive all of the packets. Some packets were dropped because the incoming rate was too high. However, the number of packets it's received and number of packets it's sent out are more or less the same. So here we can see that the packets that the L2 forward application sent back are received by this load generator. So this figure is 1939 something, and it is also 1939 something. So the number of packets sent and packet size including headers is 642 bytes. Why 642 bytes? So 600 byte is payload. So I'll show you here. 600 byte is payload, then 8 byte UDP header, then 20 byte IP header, and 14 byte Ethernet header. That makes it 642. So here we can see what was the packet received by our L2 forward application. So this is the 14 byte Ethernet header. Here you can see the two MAC addresses. This is the destination MAC, and this is the source MAC. So this, as this was sent by the load generator, so the destination MAC will be that of the application running the L2 forward, that of the server running this L2 forward application. That is, this MAC, this is the MAC of this server or the interface which is bound to DPDK, and this is same. Then there is 20 byte IP headers, 8 byte UDP header, and the rest is payload. Once we receive this packet, here you can see that the MAC addresses are swapped. So the destination MAC here in the received packets becomes the source MAC in the transmitted packets. And the source MAC is swapped to become the destination MAC. And the remaining packet is unaltered. So once that is done and the packet is sent back to the load generator. So here we can see we have sent this many packets. The size is 642 bytes and experiment time is 30 seconds, and it is approximately 33 Gbps. So the link is 40 Gbps, and we have almost saturated the link. So with other headers, with other packet sizes, we can saturate the link. Okay, so that was the demo. Now let me explain a little bit about what was going on there. So as you may have noticed, there are certain command line arguments while I ran the L2 forwarding application. So these are the command line arguments. Okay, so I'll explain them one by one. So -w is whitelisting the port to be used by this application. By port, I mean the interface of the NIC, and this interface is bound to the DPDK. By -c, we are giving the core mask in hexadecimal. That is, we are specifying the number of cores to be used by our application. Here it is 1. So these are basically EAL parameters. So what are EAL parameters? This link explains it in detail, but I'll explain it in a few words. So EAL is Environment Abstraction Layer. So this EAL is provided by DPDK so that developers can use, so this EAL is used as an abstraction layer so that the developers doesn't have to concern themselves with the inner complexities of the DPDK drivers or what is going on inside the DPDK code, actual DPDK source code. So the developers have provided APIs, and we just use these APIs to manipulate our to write our application. So this EAL provides us with APIs and easy, as you can say, interface to interact with the DPDK, with the DPDK libraries, with the DPDK framework. So there can also be application specific arguments that you can pass. For example, here it was -p or port mask in hex, so specifying the number of ports to be used. Note that port and NIC is the same. So in DPDK terms, we call NIC interfaces as ports. Next, I'll explain the code a little bit. So first, for any DPDK application, we have to first initialize this EAL. This should be the first API to be called in any DPDK application. So it initializes the EAL and makes way for the application to use the DPDK framework, this RT EAL init function. So here it takes two arguments, argc and argv. So we have all written C or C++ programs with argc, argv arguments, parameters to main. So it is the same. So it just additionally has the EAL parameters along with the application specific command line parameters or command line arguments. So this function on success returns the number of parsed arguments. That is, on success, the EAL arguments are already parsed, and now you are free to parse your application specific arguments. Next is setting up the ports or queues. So this has to be done before actual data transfer. So here we set up how many queues to use, how many. So we configure our ports, we configure our TX and RX queues, and so on. So first we call this rt ith dev configure, where the NIC port is configured by this API. So we set the number of RX TX queues, whether the NIC should perform RSS or not, and so on. Then we set up the TX queues, where we tell how many TX ring descriptors to allot, what TX offloading feature to be enabled, etc. Similarly, we set up the RX queues. So by offloading feature, I mean that some processing is offloaded to the NIC instead of doing in the user space. So I'll be discussing about offloading in a little bit more detail in the next, after 1 or 2 slides. So finally, we start the respective port via this rt ith dev start. So this port can now start receiving and transmitting packets. That is, it will, once we call this API, now when the NIC receives, we can transfer those, when the NIC receives packets, we can transfer those packets to the user space, and again, we can also send packets from user space to outside via the NIC. So you can check out in detail about these APIs in this link, and we'll now move on to the APIs provided by DPDK for actual receiving and transmission of packets. So these are the APIs. For receiving packets, DPDK provides the RT-ETH RX burst API, where we specify from which port and which RX queue we want to receive the packets. The packets, we also pass two other parameters. One is packet burst. Is an array of RTMBuf structures, that is an array of structures to store the incoming packets, and we tell the API what is the maximum number of packets we are expecting at a time. So the actual number of packets is anything less than or equal to this maximum packet burst. Similarly, while transmitting packets, we use RT-ETH TX burst. Here again, we specify from which port and TX queue we are going to send out the packets, and the packets in the user space are stored in this array of structure, packets burst, and we also specify how many packets are to be transmitted maximum at a time. So the actual number of transmitted packets is anything less than equal to this max packet burst value. As you may recall, this RTMBuf structure was discussed in the previous lecture as well. So this RT-emboss structure is a structure similar to the kernel's escape buff. So now we move on to the offloading features on and now we'll talk about DPDK and how we can take help of modern NICs and offloading features to improve our application, make our applications more efficient. So DPDK provides many APIs to take advantage of the features on the NICs, on this modern NICs. Some packet processing can be offloaded. For example, checksum verification or computation. So we can manipulate any headers, we can manipulate data. However, after we change the data, we have to compute the new checksum. Otherwise, the receiver won't receive the packets because of incorrect checksums. But computing checksum in the user space is a heavy task, and it will slow down our application. So what we can do is we can offload this processing to the NIC. Similarly, distributing packets to given RX queues based on particular header via RSS, then parsing IP or UDP headers and taking some simple actions in the RSS itself. Say, for example, we don't want to receive any packet coming from a specific IP. So we can tell the NIC to drop all packets when it comes from that specific IP. So all these simple actions, simple functions can be performed in modern NICs, and it helps us to make our DPDK application more efficient. To check or set what offloading feature the NIC has, you can either use this ith tool command, or DPDK also provides APIs. So this link provides an easy startup guide if you want to write your own DPDK applications. So how to start with your compiling and installing, and then how to code your own application. So while compiling your own DPDK applications, while compiling our own DPDK applications, we have to set two variables, two environment variables, RT SDK and RT target. Once those are set, then we generally compile our application using make, and the application executable is stored in this path. So if you want to make any client server type application, so there are some common packet generators that are available. So for example, iperf or DPDK itself provides a very good application, testpmd. So you can check this out. So testpmd is not only a packet generator, it does a lot of things. So it is a very good starting point for beginners who are trying to write their own DPDK applications. If you're interested, there are many links provided in this slide for further reading. So DPDK explained in simple terms, then overview about DPDK APIs and data structures, some user guides about applications, all those things are here. Also, there are other applications which use DPDK, or say for example this user space TCP stack discussed in the last lecture, like mTCP and so on. So if you are interested, you can check out these links. That's it. Thanks.